So there is this fundamental question that we had. Given n, yeah, given a natural number n, yeah, how many numbers less than equal to n or less than n and co-prime to n? Yeah. Now this is a function of n, right? Just a function in the sense that this depends on n, right? It varies with n, obviously. And this is usually has a notation. It is also called, I mean, that is traditionally denoted by phi of n. Okay. And just before we get into this, finding this more explicitly, let's just remind why this is important. So can somebody tell me first why this is important? Why this number, I mean, why this number is relevant for us? It's an interesting question on its own, but why is it relevant to us? Yeah, I think, or how did we come to, like, talking about this number? Okay, not a to the n minus 1, but yeah, so when n is equal to p, so we had this following theorem, right? And this we had seen last time, and this is Fermat's little theorem, and this has many applications. If you just see any number theory book or just Google problems in Fermat's little theorem, you get plenty of small simple exercises to begin with. This we know is true. P is a prime, obviously. But then we had tried to take this argument further. Yeah, we tried to take this argument further and we got something like this. We got, so last time I had used the notation F, yeah, because we wanted to, say it like we are doing it or, but obviously now that I've used this notation, I'll continue to use phi n. We had proved this, yeah, and I'll just do an example for this so that it becomes more clear. Yeah. But what does this mean? It means that you take any number a, and when you raise it to this some power, this special power, which is the number of numbers less than n co-prime to n, then this number is actually congruent to 1 modulo n. It leaves the remainder 1. Okay. So is everybody on the same page that this is what we had seen last time? So, but it is true for any a. Yeah, any a that is co-prime to a. Yeah, and that's is that what you're asking? So at a particular time, yeah, we have to put some a, but the good thing is that this is true for any a that is co-prime to n, and the power doesn't depend on a, right? And it's like just for the Fermat's little theorem, the p minus 1 works regardless of whatever a you choose. Right. I mean, other than the obvious exception that it cannot be p or 2p or multiple of p, right? It works. That's the beautiful thing. That's why it's a theorem, something that works for a large number of sentences, a large number of statements, whatever. Yeah, that's why it's a theorem. Yes, but obviously we have seen again this thing earlier that this p minus 1 need not be the smallest power. Okay, but we'll not get into that now. Similarly, this phi n, and this is a beautiful thing, right? The phi n only depends on n and does not depend on a. So you might as well say that a is not a specific number. I mean, it's like a variable kind of. Yeah, that's why it's a theorem, which is saying something both about a and n, yeah, general. But then we agree that this is what we had proved last time. We started with an arbitrary a and we kind of did the arguments, right? Took the size generated by it and so on. Let's not go into the proof now. But let's do an example. Can anybody illustrate an example of the second statement? Yeah, so maybe because it's still, yeah, it's very nice to. I mean, such a surprising, such a nice statement, but we should see an example. So can anybody 4n? 4 and 5, yes, but I want to take something which is not a prime, right? Because then only it will come out that the second is true. Otherwise, it's just one only. So we should take n which is not a prime, right? So we can take, so what can we take? Yeah. So you can say, for example, 6 and 35. Why not, right? Take 6 and 35. So then we'll have some interesting calculations to do. We have 6 and so none of them are prime by any means. Yeah, but they're co-prime. And we take n equal to 35. Yeah. Well, the first challenge is, this is basically what Aparna will maybe tell us how to do later. But first, let us at least find it. And so maybe you can match your method also here. So what is phi of 35? Yeah, so here phi is not the empty set. It is just a notation that it's a function. It takes some input and it returns. Yeah? It depends on the 35, 36, it will change. So what is phi of 35? How many numbers less than 35 are co-prime to 35? Yeah, take your time, do the calculations. This does not need any, yes, you can just do the calculations. Just tick off the numbers that are, less than, say, co-prime and just tell the answer. Let's see what others are saying. I think it cannot be 23, but maybe you have missed some numbers. Getting 22, and I think, okay, let's see what others are saying. So you guys are missing a few numbers, just one or two numbers. Yeah. So you can try to apply, you can just try to count just naively, or you can also, if you know some method or some formula which you have seen or something, try to apply it and see if you're getting same answer or what you're getting, match it. Others, Pragdish and Nagesh, can you tell how many numbers less than 35 are co-prime to 35? I mean, there is a formula which one will prove, but one should have to calculate it directly, because most things you don't have formulas. We don't have any formulas for most things. And while doing these calculations for many of such examples, you will see a lot of patterns and you'll get a hunch of, you'll get estimations and so many things, which you can later convert to theorems. Yeah, because 35 and 35, but 35 also, that obviously doesn't work. So yeah, less than 35. So yeah, so it's not 22 or 23. Come on, so others have not calculated. Just tick off the numbers, right? I mean, one. Yes. 25. No, 25 is also not correct. That's also missing by one. Anyway, so the answer is 24. So, so it's just Pragdish, have you done the calculation? Just count the numbers, right? Just like one works, two. So one, I mean, just one, two. You can just do like this. 3, 4, 5 is the work. 6. 7 doesn't work, 8, 9, and so on. Right? Just you'll get 24 numbers. Okay. All right. Anyway, so this is for now 24. We'll investigate this function more later. Fortunately, this function has, fortunately, because for most functions you don't have, but for this function you have a very nice thing. Okay. Anyways, yeah. Now, what should we check? We should try to calculate. Should try to calculate 6 to the power 24 and see what remainder does it leave. Yeah. Modulo 35. This is not difficult. Explicitly we can check. Yeah. So you guys have done this thing earlier. Like you do 6 square, right? And you see 6 square is 36. It's equal to 36. But 36 is just 1, right? 36 leaves a remainder 1. And then we have seen these kind of things earlier, that now you can raise both sides to the same power, right? So you can raise both sides to 12, right? And you get 6 to the 24 is 1. So indeed it works. Yeah. So that is what the theorem also told us. Obviously, I mean, the calculation tells us much more in this specific case, that in fact 6 square is 1. So that's a much better statement in that sense. But still, the theorem is telling us in general that that you could do it for any a that is coprime to 35. And that is something. So now, is there more belief in this statement too? Even though we have seen the proof, but you see, it is correct. It works. All right. Yeah. Okay. Good. All right. So then that is the thing. So now what is it that we should do next? Yeah. And so just going back, these calculations are fine. This is something that you have to just practice. That is, you to practice more and more of. But what was the key point in this? In this basically the key thing why this proof worked. I'm not going into the complete proof, but this basically implied that you take a, 2a, 3a, na, yeah. And when you consider the remainders of all these, because they may be more than n, when you consider the remainders of all these modulo n, then you recover all the remainders. So 0 is the n. I mean, this was the key. And this will be the key later in many places. You do complex numbers, at least many places. This is the idea that something that is cyclic, yeah. This is a cyclic thing, right? This is a cyclic thing. I mean, these numbers are cyclic. You start with 1, you add 1 to it, then you add 1, you get all these numbers. You go till n, you get 0. Then you add n plus 1, that is just 1. So this is a cyclic thing. It is generated by 1, certainly. But what other things generate? So anything that is coprime also generates. This also we had seen. I hope you have seen more examples and tried. And that is the reason why this proof worked. Yeah. So the beginning of it, right? And then we basically took a subset of this, but let's not go into the proof. So the key was that this A is a generator of Zn. Yeah. And so my point in saying all this is that this question is important, at least here, is because this number is the number of generators of Zn. And later on, you will see many other applications of this. So this is also equal to number of generators of Zn, meaning, this set of numbers which we had this nice arithmetic where you do things by taking remainders, Zn. Yeah. I mean, this has many other interesting ways to be seen. For example, if you look at, if you suppose just a minute. Yeah. Suppose I make a hexagon. Okay. So this is a regular hexagon and everything. Everything is as good as you can imagine. Center is at the origin and so on and so on. It's a regular hexagon. Now, the moves are like this. Okay, suppose you want to start from here. Suppose this initial thing, one thing I'm telling you that if you start from here, so let's call this 1. Let's mark this. Yeah. If I start from 1, and then the move is that at each step, I can only jump to just the next vertex. Okay. Okay. So if I do that, then I'll go to 2, and then I'll go to 3. Okay. I'll visit all the vertices, right? Yeah. So now the question is, okay, we are always starting from 1. That is always given. The question is, how much angle can I jump by? Yeah. What are the allowed angles by which I can jump so that I can do the circle? So that I can cover every vertex. So I'm not framing the question properly. My point is that if I start with 1 and my jump is 60 degrees, then it implies I can visit all vertices, right? But then the question is, if I jump by 120 degrees, then can I visit all the vertices? Can anybody tell? If I jump by 120 degrees at each, so I have to fix that. Yeah. Then can I visit all the vertices starting from 1? So the answer, yeah, right. So we cannot visit all the vertices because from 1 you will go to 3. Yeah. And then from 3 you will go to 5, but from 5 you'll go back to 1, and then it will repeat, right? So when you jump by 120 degrees, you cannot visit all the vertices. But then if I jump by this, the next thing, 240 degrees, then can I visit all the vertices? Again, starting from 1 is fixed, and the amount of jumping now is 240 degrees, or you can say skipping 2 vertices. No? Yeah, right. So why is it that? Because we will go to 4, and then you'll go back to 1. So yeah, sorry, certainly that doesn't work. Yeah. So now that's what I'm asking is that what degrees work? Yeah. So 120 and 240. Yes. So I start with vertex 1, and then I rotate. I should just say rotate by 60 degrees. At each move is rotating by 60 degrees. So if each move is rotating by 60 degrees, then I come to 2 at the second move after the first move. And then after the second move, I come to 3. And so I visit everything, right? But yeah, so that's okay. But then if I jump by, yeah, that's the same thing. Now, but if I jump by 120 degrees, or if I rotate by 120 degrees, then in my after first move, I'll come to 3. Then after the second move, I'll come to 5. But after the third move, I'll come to 1. But then again, I'll keep going to 3 and 5. I will never visit 2, 4, and 6. Right. So I am looking for an angle such that rotation by that angle will help you to visit all the vertices at some point. So can anybody tell which angle will make you visit all the vertices? 60 degree certainly works, but is there any other? 60 degree certainly works, but is there any other degrees by which you can jump, by which you can rotate? Yes. So 30 is certainly a valid answer. I mean, in a sense, so far as what I've said, but let me also put the condition that, because that's what I want to put the condition that you want to go to vertices only. You cannot. So let's say these are empty spaces. Yeah. Let's say these are not there. Right. Yeah. No, if you're just rotating, right, you cannot go to the center. Yeah. So 60 degree doesn't work, 120 degree doesn't work, 240 degree doesn't work. Is there anything that works other than 60? Think. Um, yes, 300 degree works, right? Because when you do 300 degrees, then where do you come? You come to 6. Good. Yeah. And again, if you do, I suppose you come to 5, right? I don't know. Yeah, something like that, right? So 1 goes to 6, and then you go to 5, and then you go to 4, and then you go to. So it's a reverse. It's happening in the reverse way, right? So it's like minus 60 degrees, and then 3, and then 2, and then 1 again. Yeah. So that is the other 60 degrees work and 300 degrees work, right? So these two are the generators of this move, right? Does anybody see similarity of this with and these two, what we have been doing and what this is the same thing? Can anybody make that precise, or does anybody see it, the similarity? Vague similarity, I am expecting somebody and people, at least some extent you see, right? Yeah, there is some, but there is something that you have to capture, but it's already clear that there is some similarity, right? So like if you take Z6, then what are the generators? One is a generator, certainly, right? One is a generator because obviously with one you can just get, 6 is a 0. But you start with 2, what do you get? You get 2, 4, 6. That's all. Again, you get 2, 4, 6. So it doesn't. But then we know that they will not, but we know that the co-prime things will work, right? So you take 5, and 5 works, right? Because 5, and then you add 5 to it, you add, you get 10. So 5 plus 5 is 10, right? And that's 4. Then 10 plus 5 is 15, that's 3. And in this way you get and then you get a 6, whatever. Yeah. So 1 and 5, which are co-prime to 6, are the generators of Z6. And here also, basically, it is the same thing. You can see. Yeah. But still, to capture it, to say it in a proper way that these two are the same things, that's a, So, I mean, how do we say that they're the same things? Well, let me erase this thing first. Yeah. So first of all, Z6 is the 0, 1, 2. Let's say it from 0, 5. Yeah? And here we have 5 vertices, and the goal is to cover all the 5 vertices by the move. Here the goal is to cover Z6 by a move, where the move is just start with the number and add the number to itself, right? So here we know that if you start with 1, right, and add 1 to itself, then you get everything. 1 plus 1 plus 1, and like this, you get everything, and you get 0 also in the end, right? Yeah. So no, before I say this, let me first say how these are similar arithmetically, right? So see, I mean, how these sets are similar in the sense that, so here, one second, here we have 6 things, right? And the way we are adding is, I mean, you just take 2 things and you add them, and then you consider the remainder and divide it by 6, right? Here also, here adding is like rotating. Okay, so you could yeah, so suppose you say that I will rotate by 60 degrees plus 60 degrees. Yeah, so that is like adding 1 plus 1. In that world, it is like adding, it's like taking the 1 and adding 1 with itself. Yeah, and here it is like, you know, starting from 1 and jumping here and then going from 1 to 3. Okay, now this one and that one is not the same. That's the, okay, that they are not the same things, right? But the yeah, they are not the same things, right? But the point that I'm trying to make is that the way the addition is happening here, the addition is also happening here in the same way. Okay, but well, I can make it maybe slightly more easier in the sense to explain. I can just relabel these from 0. That's better, right? Now you can see that they are the same things, right? I mean, like if you take 4 plus 5, what does this mean? So what it there, it means you go to 3. I mean, you go to 9, which means it's 3. 4 plus 5 is 3. Here, what will 4 plus 5 mean? Here it will mean that you jump 4 first. Yeah. So you start with 0 and you jump forward. So you go 1, 2, 3, 4. You go to 4. But then you jump 5 vertices from here. So it's 1, 2, 3, 4, 5. And then you come to 3. Now these two, there is no distinction between these two systems. Okay, and that is my point. There is literally no distinction. I mean, one can say it more properly, but for us this is fine. There is no distinction. Yeah, so basically starting with what angle or rotating by what angle repeatedly makes you visit everywhere is the same as start what number generates G6. And not surprisingly, the answers were same. Obviously, the angle things have been multiplied it by 60 degrees, but really the answer was 1 and 5. 1 was a 60 and 5 was a 300. Right. Jumping one vertex or 60 degrees. That is just a unit system. You can divide by 60 and yeah. So is this point okay? That this generator thing, the point of this was that the generator thing comes up in many different disguises in many different places. It come in all sorts of places. Okay. And the main thing is that the nature of it will remain the same. If you can see the similarity, then that's it. The nature of this thing will be the same. Okay. All right. When all these things are abstractly studied properly, but that is not needed now. So, all right. Okay. So that's was, I think I was trying to make a point on the what the number of generators means and how it connects with phi n and how it connects with other things sometimes. Okay. So now, as we said at the beginning of the class, the question is to find a way to calculate the number of generators. Now that this becomes a very important question, right? To be able to find the number of generators of n, of Zn, or to find the number of numbers co-prime to n and less than n and co-prime to n. Okay, how can we find it? Yeah. So I think Aparna was saying in the beginning that there is some method. So let's see. Yeah. Can you tell us? Yes. Okay. That's right. That's right. Yeah. So you're saying basically that the number of numbers less than n, which are co-prime to n, which they will not have these p1 to pk in their prime factorization. Okay, that's different way of saying that. But what you said exactly is that they will not be these prime factors or multiples of these prime factors. Yeah, that's the same. That's right. Yeah, so let's see. Let's put it to use and see if we can, using that, develop an effective more. Yeah. So that's the first idea. As you're saying, what you're saying, we will use that as the first idea and try to build it. There are many ways, but I will try to build from what you guys say, because that's the good way. I think better. Let's take some example. So okay, 7 and 5 we have already done. So okay, let's actually take 7 and 5. No problem, because we just calculated it, right? We just calculated it by hand. So so which numbers less than n are co-prime to 5 and co-prime to 7? So if we use your idea, then the numbers, you're saying that the numbers should not have 5 in their no. So yes, they should not be. Yeah, right. You're saying that they should not be this and should not be that, something like this, right? Yeah, and its multiples. Yeah. So you see, the general nature of your statement is it should not be like this. Yeah. So let me put it for everyone. We can see this, that what we are more it seems like, what at least from what Aparna is saying, we are more comfortable in calculating n minus phi n. Right. And this is an important observation to make. Complementary counting, right? Which numbers are not co-prime to n and less than and not co-prime to n is we seem to be more comfortable in calculating that, as I understand. Yeah. Is everybody understanding this? Yeah. Because I mean, what Aparna is saying is that, I mean, you calculate those numbers which are 5 and multiples of 5, and those numbers which are 7 and multiples of 7. And obviously there will be overlaps and you have to think about all that. But then just subtract this from n and that's your answer. Yeah, Aparna, is that the what you're saying? Right. Yeah. Now, yeah. So now we will use this to make a formula for phi n. Let's see. Okay. So it's clear, and this is the thing, and one must appreciate that there is something non-trivial about complementary counting. Complementary counting is not just okay, one of the ways to do the problem. No, you cannot, sometimes you cannot avoid it, as I understand, right? Sometimes counting the complement of a set is really the game changer. Let's just put it like that. So what we are going to do, so let's erase the generators and all, because the focus of the problem is now not this. Yeah. Yeah. Let me first write the idea, then we'll do it for 5 into 7. Then we will try to make a theorem out of it. Let's see. Okay. So what we will count is number of k, that hash represents number, the size of the set k, such that k is less than n, less than equal to n now. Yeah. And GCD, let's write GCD. GCD of k and n is not 1. This is what we actually will do, count, because this seems to be the more comfortable thing to count. I mean, that's what we are really saying. Yeah. It is not this and not that. So let's count that, which we are seem to be more easy counting. Yeah. So this. So how do we execute this in this case? Please tell anyone. Let's execute this idea in this case. Yeah. So I mean, so we just take numbers which are, so numbers whose GCD is with k is not equal to 1. Yeah. let's break it further, or let's not break it further now. Let's just do it in this case first. Okay. In this case, it's easy to see, easy to break it. With numbers which GCD is more than, is not 1, it means that it has to at least be a multiple of 5 or a multiple of 7, right? So this means that K is a multiple of 5 or a multiple of 7. You can follow or not follow that notation. That's not important, but is that right? Yeah. We're looking for numbers which are multiples of 5. It has to either be a multiple of 5 or a multiple of 7, right? So let's write all the multiples of 5. We have 5, 10, 15. Yeah. And then we have to take the union of this, because these are the only, this is the only way. My point is that we are further breaking it down on the level of primes, which is the only natural way to do it, right? GCD is not 1 because of some prime which comes and becomes a factor of that number K, which is common with N, right? That's the only way. So then we have 7, and for 7 we take this. That's M5 and M7. Yeah, this first thing I'm just calling it M5, and it's, you can see that it's not a bad notation. Yes. So in fact, you can take it less than N. Yeah. Yes. It. Yeah. So in the end of the day, it comes. We get the right answer, right? Because even if you do take less than equal to N, but we are going to subtract this 35 that we have taken, it's fine. But then still, I mean, why did we take it? What is wrong if we don't take the N? So the reason. No, actually, yeah. So if we don't take it, then also it's fine. Then you have to subtract it from 34. Yeah, that will also work, because nothing after the maximum multiple will be having a factor or something. But either ways, I think it's okay. Doesn't matter, because as Shana said, you have to subtract it from the, yeah. So now what is the, but actually we have written this fine, but we don't actually need so much information. We just need the number. So that's what we really are going to do in the end. But then what's the size of this set? Are we getting the 11 numbers? Good. And so what do we need? Phi n, right? This phi n is actually n minus this, right? Because this is the number of numbers here. GCD is not 1. For GCD 1, you have to subtract, right? With those other numbers as the ones with GCD 1. And so, okay, so in this case, sorry, this case is just, right? And this is indeed the right answer. Okay. But still, we have done a lot of extra things. So right now, I'm not trying to go directly to a theorem or something. Okay, we don't know if this method is good enough to get at a theorem, a formula, or even if there is a theorem, we don't know, right? I mean, for so far, we suppose we don't know, right? But what is something extra that we have done? You see, to even calculate M5, we don't need M5, right? We just need the size of M5. Is that right? Yeah. So what is the size of M5, and how can we say it directly? How many numbers less than equal to 35 are multiples of 5? Well, that's just 35 by 5, right? That's just a straightforward thing, right? Yeah, numbers less than equal to n, which are multiples of d. D, 2d, 3d, you go till n minus d by n minus n by d times d is n by d, right? This is even a divisor, so it's straightforward. And then this is just 35 by 7. Yeah. But then if you only know these things, then how do you calculate the union? Yes. So then how do you deal with that? we have to subtract something, right? So what do we have to subtract? The overlap, right? And so we just subtract the overlap. And so what is the overlap? What is this? Well, these are simply the multiples of 35. In this case, it turns out to be easy like this, but you agree, right? Something which is a multiple of both 5 and 7 is a multiple of 35. And these are exactly the same things, right? So we have to just subtract the overlap. In this case, the overlap is easy, but you know that this is the method. 5. So M5 is 7. M7 is 5. And M35 is 1. So that's 11. So we never needed to at any point write this. It was not needed. Even the intersection has a nice meaning in a similar way. Yeah, the intersection has a nice meaning in a similar way. Okay. So then how do we take this forward into making a theorem? So let's do one simplification, I think, is just let's just look at two numbers. Yeah, we don't need to go to three numbers. I mean, in the sense that, sorry, let's just look at two prime factors. Yeah. So how do we execute this for two prime factors? We have all the ingredients. Yeah. Or even, let's take it one step, even one smaller step, is we just take the same primes even, and though you know that doesn't matter. Yeah, but it matters in the sense of psi, but method. So how do we calculate phi of n of this, or how do we calculate the number of numbers which are not co-prime? So how do we calculate this? For this given n, how do we calculate this quantity? So is there any idea? Well, it should be the same method, right? I mean, if k is a number whose GCD is with this n is not equal to 1, then how could, and what is k? So k has to be either a multiple of 5 or a multiple of 7. It's the same thing, right? Do you agree? Yeah. I mean, k is there is just no other way, right? This is, k has to either be a multiple of 5. It could be a multiple of 5 square, that we don't know. Huh? But k is a multiple of 5 or a multiple of 7. Yeah? So k is in M5, well, with the n, M5 with the n. So, or k is in M7. It is just simple, right? So now what is M5 in this case? So what is M5 in this case? Anybody tell me? No, why? Just n by 5. Why 5 to the power alpha 1? No, but what do we want? We want those numbers which are multiples of 5, right? So what are the multiples of 5? Just multiples of 5. Right. I mean, if you just consider the number n, and if you just take the multiples of 5 until you go to n, so it's just n by 5, right? Does everybody agree? Yeah. Is it clear, Ishana? Is it clear? Others? Yeah. Right, Pragadish, is it clear to you? I mean, given any number n, how many multiples you have to take to get to n, right? N by 5, right? That's a number of numbers, yeah. So you see, this doesn't depend on the power, right? That's the good thing, and that's why this is such a nice formula. So you get n by 5, and then again, I mean, M7 is again n by 7, and then what is the intersection? I mean, how many numbers are both multiples of 5 and 7? Well, they're just multiples of 35. And then again, it's just n by 35. You see, this is the same thing. There's nothing different, okay? And so what we want, this thing, yeah. So this thing here is going to become, so what will it become? Well, it will just become M5 plus M7, the simplest kind of counting we are using. Nothing else, right? It's just n by 5 plus n by 7 minus n by 35. And that's the answer. It is always like this. See? It is very simple. When you have 3 numbers, you just use inclusion exclusion for 3 variables, for 3 sets, and you can get that, right? It's not difficult. You would know what you have to subtract and then add and subtract that to approximate to the answer. So this is it. Now, but can anybody arrange this in a more nice way? So this alpha 1, remember. So this becomes like this. And so this n by 7 becomes alpha 2 minus 1. Yeah. And then this last thing is just this, right? I mean, these are some small things I'm doing. Okay, this is just to get to the thing. The standard way in which it's written, the standard way in which it is written is this. They take the alpha 1, alpha 2 common. And so when you do that, then what do you have to do? You have to do 1 by 5, right? And then when you take, well, so I forgot to subtract something. Yeah. Okay, no problem. So this is the, then so what do you get here? You get this. And then you get minus 1 by 35. This is convenient, right? Because these are just the primes that are coming with the powers, no powers featuring. Okay. So you can understand that the nature of phi n is dependent on the prime factors. Yeah. The nature and the scaling happens with the power of the primes. The more power you raise, that doesn't seem to affect the nature of phi n, but just the size of phi n it affects. Okay, but the primes that you have, that affects the, so it has a certain flavor, and that's why there are a lot of problems about phi n, interesting problems, and some of them are not solved yet. Nobody has solved. So these are the things. So then what is our actual answer? What do we actually need? What we actually need is n minus this. Okay? I'm just writing this because eventually what happens is we get a very nice form, very nice formula. Though we come to it by this rather, when you do it for 3-4 variables, it becomes very messy. But still, when you arrange it, it becomes nice. So it is this, right? This is what we actually need, is our actual thing. So it becomes this, right? 1, and but then you see that this really has a nice factorization. Can anybody factorize this thing? So I've just not done anything, right? Just taken this thing common. So point is that even if you replace this by P1 and P2, this will just become P1, P2, and then still also there is a factorization. Yeah. So it is easy to check. I mean, you can just check this, that it just factorizes nicely. It is just 1 minus P1 times 1 minus P2. And this is just check. This is a standard, is important factorization in fact for exams. You know, small, they have tiny equations on. So we have the formula. We have a nice formula. Okay. For phi n. 1 comma n meaning 1, but 1 comma n is a number. 1 and n. Oh, 1. You mean 1? The number 1. Yes, the number 1 will obviously come, right? Because see, the number 1 never came in any one of these, right? It should come, right? It should come in that. Yeah. And I mean, it matches with the answers also, right? And the method, if you look at the method, it's just correct, right? Because we counted those cases which were not co-prime to n. And obviously 1 was. And so when you take the complement, then the 1 comes in the complement. Right. Yes, exactly. 1 will never come under k. And we didn't, and when we were counting this case, the 1 was, we didn't count 1, right? We just counted the multiples of 5 and 7. 1 is not there anywhere. So 1 comes. And the method is correct, obviously. So it comes naturally. And so this is the thing. Yeah. And then you have to just apply inclusion, exclusion for more variables, which maybe we'll do sometime later. Okay. And then you will see that when you have 3 variables, I mean, not surprisingly, this becomes 3 and this becomes this, and it goes on. Okay. So we started with this very basic idea, right? We made some small observations and it's all elementary. Yeah. So yeah, so this is a very interesting thing, right? So we have this for any kind of cyclic thing which lasts for n steps before coming back. These are the number of generators. There are this many numbers from which you can start with, and you still get the whole thing if you take steps of that size. Yeah, it's a beautiful formula. Yeah. So let us just quickly apply it for small examples. So are there any questions? There are many questions that come out from here. No, n is not a generator of n. Sorry, why do we take? Yes, so you can do that. You can take k less than n, but see what we did is we took what we have done here is, and let me say why this is correct. And then what you're saying is also correct. One can do that also. You'll get the same thing in the end. But what we did here is number of numbers that are less than equal to n that are not co-prime to n. Yeah. So these are, let's write it clearly. No, GCD of 0 and n is not 1. It is n. Right. Yeah. Right. Okay. So does that answer your question? Okay. But I mean, you could also do like that. You could remove this and do like this. But see, the problem with this is that then finding the number of numbers less than k which are co-prime to n, that's a little bit, you have to add some extra plus minus 1 at each step. Okay, so if you take the prime factors of n, let's say 3 is the prime factor of n, then the number of numbers less than n, which is multiple of 3, that will be n by 3 minus 1, because you're not going to take n. And it'll get the same answer in the end, but it's just an unnecessary calculation. So you'll have to do. So it's just an adjustment. Okay. So it is very, but there are many other more elegant and more insightful ways. This is not a very insightful way, because see, finally when you get the answer, it doesn't bear much connection with the method. Yeah, but the answer seems to suggest a lot of other things, which we will see when we have the right relevant context. The answer suggests a lot of special things that you can see, right? Because this is like, this is phi of P1, and very nicely, they have separated themselves. The part of P1, you can separate it, part of P2. So it kind of, for P1 to the power alpha 1, what you get, that multiplies with the power, part of p2 to the power alpha 2, and similarly, right, it separates and each part separates and multiplies to get the answer. But that our method doesn't suggest. Some strange factorization and some, just brainless counting sort of way. It's just a simple counting, right? No sort of combined work. So, but there's no number theory inside into this. But phi n is number theoretically, it has very interesting features, but we shall see that later. So let's quickly use this to calculate phi of 40, maybe, yeah, phi of 40, phi of 40, calculate. This is called the Euler's Torsion function. Yeah, so you can read more about it if you want to. Euler's Torsion function. I'll just plug the charger. Just apply the formula, you will get the answer. Right? Yes, you're getting 16. Okay, right. So let's check it. Yeah, so it should be 16. So now it becomes very easy, right? Just 40 by 6, 1 and 3. You see, they cancel out always. Yeah, this may not look like a very interesting thing. Okay, does look like a prime. It does look like an integer, no problem. Because this p1 and this, it cancels out. So anyways, point is that, yeah, it is 16. Is it 16? Right? So no, 20, right? Coming out with, no, what? No, it's right, yeah. Is it right? 2. Ah, yeah, it's not, yeah, right, sorry. How did I do? Where did that come from? I don't know. Whatever, yeah, you get 16. Yeah, 4 into 4. Nice, right. Yeah, 16. And yeah, and you can just use this method. I mean, you can use this to, for example, if I just ask you, calculate 27 to the power 1000, find the remainder of this when divided by 40. You'll find numerous exercises like this. So this, So you want to find the x. Okay, so why do you think it is 1? Three raised to 4, not raised to 750, 4 times 750, you want to say? Yes, yeah. Okay. Okay. Oh, 3 raised to 4 is remainder 1. Ah, okay, okay. Okay, so that you okay, that okay, so you got it done. That's right. Certainly. Yeah, 3 raised to 4 is the remainder of 1. So that's a yeah, in this case, that helps us. So we don't need this theorem in this case. Right, this is certainly correct. And so 81 is just 1. Yeah, certainly that's correct. No doubt. Yeah, so I have nothing to say because here you see this is easy in this case. Yeah. Uh, no, but then my point was just was that I mean, okay, so this is 27. Let's say, let's try. Let's say if I make this some other number and see what. So for now, I'm just keeping it co-prime. You can think about the other case later. So let's just make it 29 and see if it's yeah. So try it out with that. So you have to try to use this. So I mean, because always I don't think you can get away without using this. So you have to use the fact that this is 1. Yeah. I mean, it will still come, but we use this, maybe it's huh. Yes, so that is fine, right? That is okay. So basically, you're saying that this 1000, so 1000 is, let's just do it for one. So 16, 6 and 96, 4, 16 to the 32. Yeah, it is 16 times 62 plus 8, right? That's what 1000, so that's what 1000 is. Yeah. And so from this formula, we know that we can forget about this 16 to the power 16 times 62, right? So that's the advantage, which is a big simplification, right? Yeah. This is 29 square 1. It might be. How much is it? Wait, how do you multiply this? 29, 18 and 8 is 20. 841. Oh, is it 1? Okay. I mean, see, yes, in again, it turns out to be 1, but just if it takes some number, like maybe 33, 33 is not 1, right? So 33. Point is, yeah, I always keep giving the wrong number. Last time, what number had we taken? 20. What was the number we took last time? 27. So you see, 27 we took. Either ways, yeah. So whatever I have, so we take 33. You see, so you see, the point of all this is that this is the way to reduce the power, right? This is the way to reduce the power. You see, the power reduces based on the GCD, based on, okay, there's a connection with GCD also, but the power reduces based on the remainder. Okay, and that is the key thing. Yeah. So whenever you are trying to figure out this power, you can just consider the, instead of that big power, you can consider its remainder when it is divided by the 16 or by this phi n, right? Because I mean, you can understand even more cleanly, or maybe I shouldn't erase this. This part is there. Can erase other things. This formula is certainly there, but to use it, what I'm trying to say is that whenever you have something like this given to you, that a to the power b is 1 mod n, right? And you want to calculate a to the power c, right? So you can rather just calculate a to the power r, right? Mod n, where this r is the remainder, right? Where b is congruent to r mod n. R mod, not b. C is congruent to r mod. So c, to say simply, the c is bq plus r. This is the major simplification, right? Okay, that you can work with the power, and you can reduce the power based on the remainder, and you can do. That is the thing. Yeah. So now you can just take numbers like this, play around, and you can do. You can just Google, Euler's Torsion function, Fermat's little theorem, and just you will get plenty of problems. Yeah, Brilliant or AOPS. I guess the initial problems will be simple. So do them. Yeah. So today we have not really seen. We have seen new ideas and done a new problem, proved a new theorem. But no new ideas for the next day seem to have arrived from today so far, right? So that is okay. That's the nature of some. We cannot force this. Yeah, I have to just try more examples. But you can see a few things from here, right? You can see that phi n is even. It at least it suggests that it is always even. It's always an even number. Okay. And what also suggests, you can see that in the formula also, is that this seems to be like this. But whenever A and B are coprime, or maybe let me just at least say this, that we are getting something like this is clear, that this is this. Yeah. And obviously you can see it in the formula also, right? As I was saying, right, that you do it for P1 to the power alpha 1, and you do it for P2 to the power alpha 2, you will get these answers. But then doing it for the product seems like you're just finding it for the separate things and multiplying, right? That is a very interesting thing. That's a very, very interesting thing, right? So this is what I called a multiplicative function. Okay. So this is another thing that it seems to be true. Okay. But then what can I ask you guys to prove this? I don't know, because in some sense you have already proven this. Once you have this formula, then you already have it. Okay, you already know it's true. Yeah, so then I don't have much to ask then, yeah, at least so far. So yeah, so I think then that's it. Let's keep this for today. Okay. You can try problems and yeah. So next day maybe then now is the time to maybe go further into these problems. Yeah. Into this exercise 2.2. Okay, and we will do that. Okay. And yes, so that's what we will do. And tomorrow, but that's not for everyone, maybe. So maybe Nagesh and Unab. So Unab is not here. So okay. We will take this. I'll